Hi folks, how are you? I hope you are okay and you have a nice morning. Please, if you can hear me, just do as always in the announcement I have just published. Thumbs up, please. Okay, I see you can hear me now. Thank you so much. So today we are going to continue with the instructions in assembly language that we have seen in the last lectures. Remember that as always, part of the material we are using here is extracted from the book. So what we are going to see today are something called pseudo instructions. Those are not actual instructions, but we will use for us, for the programmers, is like if they were instructions. Then we will move to addressing modes. We have actually seen some of them in instructions, but we will put a name to those addressing modes. And finally, we will see an overall summary on how a program is compiled and then executed in our machine, in our computer. So let's start with the introduction with the pseudo instructions. So pseudo instructions are a kind of instructions that are translated into different instructions to the ones we see when we program them. It's like if we have an additional layer of abstraction to the real instruction. This is usually to make it simple for the programmers. Those instructions, pseudo instructions, are not actually implemented. What happens is that they are just converted into real instructions. And as I have mentioned, the reason for this is that those pseudo instructions are much simple for us, for the programmers. And as I have also mentioned, those pseudo instructions, what happens what actually happens is that they are converted into another instruction. Let's see an example. For instance, we have this pseudo instruction, which is called move, which actually makes that the register 9 gets the content of register 10. This instruction is actually not implemented. So this is just for us, for the programmer, to make it simple to program when we want to assign the value of one register to another. What actually is happening is that the assembler is converting this instruction into an OR instruction, which this is made in order to you remember that we want to keep our instruction set simple. We don't want to have a lot of instructions because we have limited resources. So this is a way of making the life easier for the programmer and also using less instructions. In this case, as you know, how an OR works, we have already seen that. And for when we do an OR with, in this case, 0, remember that register X set R has always the value 0. So when we do an OR with 0 and anything, what we get is anything. So in this case, if we put in register 9 0 or the value in register 10, we will have in 9 the value of register 10. Okay, makes sense? So what actually is happening is that the move instruction is just for us, for the programmers, but in real life, we will get this instruction executed in the machine. Okay, let's see another pseudo instruction. Compare. In this case, we are comparing the content of register 9 to the content of register 10. What actually happens with this instruction again is that it is converted to this other instruction, which is just making a subtraction of both registers. Make sense? I want to highlight something in this slide. So if you see, we are saying in the first pseudo instruction in compare, we are saying that we compare register 9 and 10 and set flags. And then in the actual instruction, the sub instruction, we are saying that flags is equal to 9 minus 10. So what actually is these flags? So these flags are the condition codes that we are going to see now. And if you see, we have put an S after the sub instruction. Okay, so this S means that we are going to make this sub instruction setting flags. So those flags are condition codes that we use for different things. Basically, these flags are 4 bits, which indicate the result that is going to set a specific condition code. We have different condition codes. So the first one is the flag N, and it says if the result of making an operation was negative or not. For instance, if we go back, here we were subtracting register 9 and register 10. If this subtraction, the result was a negative value, we will have the flag N set. Okay. Similarly, we have the flag 0, which means that if I subtract, following the previous example, if I subtract register 9 and from register 10, if the result is 0, this flag set will be set. And that means that both values are equal. We can use this flag for this, which is actually what is happening with the compare pseudo instruction. Then we have other flags, overflow and carry. Those flags, we will see those flags in next lectures. But for now, just keep in mind that we have different condition codes, and that in order to use them, we need to use instructions that have these set flags on. So you can see here now some instructions that use those flags. For instance, yesterday and in previous lectures we showed that we have an instruction which was called B, branch, and it just jump to a level in the code. But that branch or that jump in the code was unconditional. Right now we have the same B instruction, but we are adding conditions. So we can say, okay, only jump if, for instance, the values are equal. How do we know if two values are equal? Because if they are equal, the flag set will be activated. Make sense? Similarly, how do we know if two values are not equal, are different, which is what we are expressing here? So if the set condition code, if the set flag is not set, this means that the comparison I just did, the numbers or the registers were not the same. Okay, I have other instructions here. So less than, less or equal, greater than, and greater equal, doing similar things. So using those instructions, I can jump or I can go to a specific place in my code only if a condition is satisfied. Okay. Let's see an example to make this clear. So imagine that we have this instruction in which we are just, as you know, assigning the value 10 to register 1. And now here I have a label loop, and what I'm doing here is I'm using the subtract immediate instruction, but with the S. So I'm setting condition, I'm setting the flags. What is doing this instruction is, apart from subtracting 1 from register 1, okay, we are also setting the flags. This means that I can use those instructions we have just seen. So I can branch to loop again and make this loop if, for instance, register 1 is greater than 0. So what will happen here? So this loop will be running until this condition is not satisfied, until as here we are subtracting 1 from register 1, which initially was 10. What will happen is that we will finish this loop once register 1 is 0, which means that we have run the loop 10 times. Okay, makes sense? It's very important to notice here that we need to use the instruction with the S, because if we don't add this S to the sub I instruction, then flags will not be set, and this instruction here will not be doing what we want. So now I have an exercise for you. So we have seen the first how to do the first instruction. So to do this instruction, go to the label loop if the register 1 was greater than 0. So from what you have seen in previous slides, what do you think are the correct values to put here? So I have a form here that, I have a form here that I'm going to add to our chat, and then you can try to answer those questions here. There in the form. The form is published now in the live event Q&A. So I give you 1 minute to answer those questions, and let's see if everything is clear. Okay, so let me check what you have answered here. So I see some of you are still answering. So for the first one is the one we have already seen, that is clear. Then the next one will be similar, but instead of the instruction BGT, we use, which is branch if greater than, we have branch if greater or equal. Okay. So then for the other one, we have that we only branch if the value is equal to 0. Then we are using here the less or equal, and similarly we have the less than. Okay, I see from what I see in the form responses, most of you got the correct results. So you can see here, most of you got the correct answer. Okay, so I think this is clear. Okay, I have a couple of questions here before we change to another thing. So someone is saying, where did the S from the sub I instruction, for instance, this S, from where it comes from? So this S comes from set flags. Okay. Then let me check. I think there is another question. So someone is also asking that if we could see pseudo instructions like in other programming language, like a macro for another instruction. Yeah, we can say that it's like something like a macro. It's something like we see as programmers, but it's actually not implemented in the code. Okay, so let's continue now with the. Okay, we have seen already this. So now what we are going to see, we have seen pseudo instructions. We are going to see addressing modes. We have, as I have mentioned, we have actually seen some of those addressing modes, but now we are going to be aware of that. We are going to add names to those addressing modes. So we have mentioned several times that keeping all the instructions 32 bits makes our hardware and our instruction set simple, and this is good because we are limited in resources. So what happens if we need to use larger values in an instruction? What happens if I want to assign a value which is greater than 32 bits to a given register? So for this, what we use is something called addressing modes. For instance, see this example. You already know the add die instruction, which adds an immediate value to a register. So if we want to add 1, okay, that's okay. I have 12 bits, so 1, I can represent it in 12 bits. But what happens if the immediate value I want to use does not fit in those 12 bits? Okay, so for this, we have two options. The first option is using something that we call wide immediate operands. We are going to see now a couple of instructions that help us in doing this, which are mov sit and mov k. And the other option is using addressing modes. So let's see the first option, wide immediate operands. So those two options, those two instructions, what do is they set bits in a register, but they send them in subsets of 16 bits. With these instructions, we can set first 16 bits of a register, then other different 16 bits of a register, and by doing this, in the end, we can set the 64 bits of a register. We will see an example later which will make this more clear. In order to indicate which 60-bit subset of one register we want to modify, we have to specify. You remember the LSL, the logic shift left instruction. We need to specify this label, and then we say, if we say 0, this means that we are going to modify the first 16 bits. If we have a logical shift left 16, this means that we are going to modify the from bit 16 to bit 32. If we indicate 32, it means that we will modify the bits from 32 to 48, and then if we indicate 48, we will modify the last 16 bits of my 64-bit register. We could see that as if we were dividing a 64 register in 4 quadrants of 16 bits, and we can modify any of those quadrants. We will see an example in the next slide, which will clarify this for sure. As I have mentioned, we have two instructions, mod set and mov k. So the first one, mod set, modifies the quadrant we have selected, and also modify the rest of the bits of the register, assigning them the value 0. If we want to keep those values and only modify the quadrant we have selected, we use the operation, the instruction mov k, which keep the values. So let's see an example to make this clear. First of all, we will see the format. Remember that we have seen different instruction formats. We have seen the register format, the immediate format, the data format. Now we have another format for those instructions, the movk and the movset. This format is called wide immediate format. To be more accurate, in this case, these instructions use a format which is called immediate format, which is basically the same as the wide immediate format, but the operation code, instead of having 11 bits, is split. We have 9 bits for the operation code and 2 bits for a second operation code. So in this case, we have the two operations. So the operation code, it will be movset or movk, will be represented by 9 bits. You know right now how to look for this code. Remember that you just need to go to our reference data, which is available on Canvas, and you can go here and say, okay, movset, for instance, is here, and the operation code for this operation is this one. Movk is here, and the operation code for movk is this one. Okay, so once we have this operation code that you already know how to achieve, we have the register that contains the data we want to modify. In this case, the destination register RD, which is placed here. Then we have the immediate value, 16 bits. The 16 bits that we are going to modify of this register of 64 bits. And then we indicate the quadrant of this register that we are going to modify with values 0, 16, 32, or 48. For instance, for movset, we know that the operation code is the one we have in the screen, and I have already shown you how to get it. For movk, we have this other one, and for knowing the value of the second operation code. So this operation code is going to depend on the value of logical shift left, on the value of the quadrant of the register that I'm going to modify. So if I want to modify the first quadrant, the up2 code will be just 0. If I want to modify the second quadrant, the up2 value will be 1. If I want to modify the third quadrant, the up2 value will be 2 in decimal, 1 0 in binary, and then finally, if I want to modify the third quadrant, I will just put 1 1 in binary, which is 3 in decimal. So let's see an example to make this clear. So imagine I have this instruction, move 0. Okay, so we are going to modify register 9. We are going to put the number 153 in the second quadrant. Okay, and for the rest of the bits in register 9, as we have here the set, we are going to put zeros. So we are going to modify this quadrant here. Okay, now I think it's clear the thing of the quadrants. Okay, so we have here in the LSL the number 16. This means that we are going to modify this quadrant of register 9. Okay, so if we perform this instruction, the content of the register 9 will change in this way. So the rest of the quadrants that we are not going to modify, the yellow ones, will have a 0. Why? Because we are using the movset, which set to 0 all the quadrants we are not modifying. And then for the quadrant we are modifying, the first quadrant, okay, we have the value 153, but in binary. Okay, makes sense? So let's see an example now, but instead of using movset, we are going to use movk for keeping the value. So in this case, the instruction is the same. We have just changed the set by the k, and what is going to happen is that we are not going to change the values in the quadrants we are not modifying. So in this case, again, we are modifying this quadrant here, okay? First one, the quadrant number 1, or if you want to go, this quadrant will be quadrant 0, 1, 2, 3, okay? So we are modifying quadrant 1, and this is the only value which changes. The rest of the values are the same as before. Okay, so let's see now examples modifying different quadrants. For instance, if I want to modify quadrant number 0, in this case, with this instruction, with the mov set, all the bits in the register will be 0, except for the quadrant 0, which I have put the number 255 in decimal. If I want to modify the second quadrant, this one here, I just need to change the value in the LSL, the logical shift left, and then what will happen is that the values in this quadrant will be modified, and the rest will be set to 0. Okay, makes sense? Let me check if I see any question here. Someone is asking what is LSL. As I have mentioned, we have seen already this in previous lectures. Logical shift left. Remember that we use logical shift left and logical shift right for multiplying and dividing. So here is the meaning. Okay. Someone is also asking if the logical shift left value is encoded in the op2 field. Yes, so we have seen here that for this instruction, let me check the slide. So we have seen in this slide that the value of the op2 code depends on the value of LSL, and is encoded here. Okay. Let me see. You have another question. Okay, so let's move then to the next kind of using I have mentioned you that we had two options. One was wide immediate operands, and I also mentioned that we can also use another option which was called addressing modes. So with this option, we can also indicate more bits than the one that fits in the instruction. For instance, we have seen that the first addressing mode is actually the immediate addressing. This is, for instance, the add I instruction we have seen before. Okay. Then there are other kinds of addressing that we are going to see now. One is called register addressing, in which the operand, instead of being indicated in an immediate value as happened in the immediate addressing, is represented in a register. We have also another kind of addressing mode, which is called base addressing, in which the operand is the sum of a base register and a constant. This is the case, for instance, you remember the arrays instructions for loading and storing data in memory. So this was the kind of addressing we were using there. And then we have the PC relative addressing, which is that we are to the PC, to the program counter. Remember that the program counter has the address of the instruction that is being executed. So we add to that program counter another address which is indicated in a constant, and we jump to another instruction. This is what we use in branch instructions. Okay, let's see examples of all of them. For the immediate addressing is clear, so we just indicate, for instance, in the at in the at immediate, we just indicate here the immediate value, and with this we can indicate up to 12 bits. What happens if I need more? So for instance, we can use the regular add instruction. In this case, we are using what is called register addressing. So the operand is a register. So it's just with this we have 60. We can indicate 64 bits in the operand. Okay. So now I think you see the advantages of using, for instance, register addressing. Another kind of addressing, the one I have already mentioned. If you think about this, we have seen all those instructions already in previous lectures. What we are just mentioning here is the formal name that we give to those kind of addressing modes. So in here, what happens in base addressing is that we have the address, a base address in a register, and then we add an immediate value to that address. For instance, in this case, we have in register n the base address. For instance, remember when we were working with arrays. Okay, so this will be the base address for the array, and then we add we add a constant to that address. In order for in the case of the arrays, in order to access element 8, in this case we need to add here the value 64, and we will be accessing the element 8 of the array placed in register in the register base x22, and we will then go to that addressing memory, and we will get this value from there. Okay. So now, another kind of addressing. We have already seen this. Remember the compare and branch if 0. So this instruction, remember that if the register is equal to 0, we go to a given address. So what is happening here is that in the program counter in the PC, we have the address of the instruction which is currently being executed. And what we do is we sum the address indicated in the address field and then go to this address in memory. This is usually used for going to an address which is indicated in a label. So in this case, remember that we put here a label. This is just for the programmer, for make it simple. But what actually happens is that the assembler is going to convert this to a memory address. Okay, so this is just for us, for the programmers. It's easier for us to use labels instead of addresses. But internally, this exit will be converted to an address and will be added to the value of the program counter, and then it will go to that address in the memory. Okay. So as a way of summary, we have here the 4 addressing modes we have seen. The immediate addressing mode, in which the operand is an immediate value. The register addressing mode, in which the operand is indicated in a register. The base addressing mode, in which the operand is indicated in a register plus a given address. And then the program counter or the PC relative addressing, in which the address is indicated by the program counter and adding an address indicated in one field of the instruction. Okay. Let me check if you have any question before moving to the next part. I'm still seeing questions regarding the wide immediate operands. So for instance, someone is asking, how do we know if we need to use the format IM or the format IW? So let me jump to the correct slide. Someone is asking, how do we know which format we need to use? Okay, remember that we have our reference dataset, and here you have the format. So here you see movset has IM format and movk has IM format. Okay, so by coming here, you see, okay, the operation code only takes 9 bits and we know this format, and with this we know the format not only of this instruction, this also can be used for any other instructions as we have seen. Okay, so this is someone is also asking what does IM format stands for. IM is immediate format and IW is immediate wide immediate format. Okay. Okay, I don't see any other question here. So let me then continue with the next point of this lecture, compilation and execution flow. So now, if you remember in the first lecture, we showed that, okay, we have our C program or Java program or a program in any other high-level programming language. So how actually, what actually happens since I have my program until it's actually executed? So what all we have seen in these lectures, in these 5 lectures, we are not now capable of knowing what is happening. So for the high-level programming language, in this case, we are using C as an example, but you can imagine any other high-level programming here, Java or any other. So the compiler translates this program in high-level language to assembly language. What is assembly language? We have seen a lot of instructions now. So those instructions in C are translated into assembly language instructions, into add, into sub, into load, into store instructions, into all these instructions we have already seen. What happens then? So once we have those assembly instructions are converted into zeros and ones by the assembler. And we have already seen how actually those instructions are converted into zeros and ones. We can do it manually. We have done that for different instructions in past lectures. Okay, so first of all, my high-level programming language, then it's converted to assembly language, instructions, add, sub, load, store, and then the assembler converts this to actual matching language, to zeros and ones. But think here, what happens? So when I program, when I develop a program, do I implement all the functions in the program? No, there are different functions that I'm using and that are available for me. For instance, if I want to get some input data from the keyboard, I don't need to develop that instruction, that operation. That operation is offered by me, but there are libraries which have pre-implemented code for getting inputs from the keyboard or for displaying outputs in the monitor. So this is what we call library routines, or it's pre-existing code that we use in addition to the code we have developed. So there is something called linker with that what is doing is we have our developed code and we have the pre-existing code, and it links both codes in order to make a unique executable. Okay, once I have this executable, is the one containing all the code, my code and existing code, and all translated to zeros and ones. What happens then? Then there is something called loader, what loads these zeros and ones into memory. Remember what we mentioned about the store program concept. So everything is in memory, instructions and data, and everything is represented in with zeros and ones. Remember yesterday that we showed how my program, how was the layout of my program in memory, that we have a region in which we have my program, then a region with static data, and then remember a region with dynamic data and the stack and so on. So this is what actually happening. The loader is putting my program in a given address in memory. Okay. So this is actually what I have just mentioned, but I wanted to have it also in the slides with text, not just the figure, because I think it will be easier for you later when you come back to the slides. So this is what I have already mentioned. The program is compiled from the high-level language to assembly language, assembly instructions. Then the assembly instructions are translated to zeros and ones, to matching code. Then this matching code is merged with other existing codes for getting inputs from the keyboard, displaying things in the screen and so on, and everything is combined in an executable, and then something called the loader loads my program, loads my matching code into memory. Okay. Make this process faster, there are some steps that can be combined. For instance, there are some tools that provide that the compiler, apart from generating the assembly code, it directly generates the object model. So from the high-level language, we get zeros and ones. We don't need the intermediate stage for the assembly language. Okay. And there are also other systems that combine the linking and the load together. So graphically will be that some compilers combine the two stages that you can see in this slide, the compilation and the assembly, and others combine the linking and the loading. Okay. So here I have, this is just for you. In Unix, for instance, there is some convention in order to name files. For instance, if we are using a program in C, the suffix for the program will be C. For the assembly files will be S. For the object files, the matching code with zeros and ones will be O. For the linked code will be A. And we are going to see now the difference between static linking and dynamic linking, but the extension for those files is different. And then in the case of Unix, the executable, if we by default is called a.out, but usually we give the executable the same name as the source file without extension. Okay, so this is what we have. I have already mentioned in the first figure with the chat, but as I have mentioned, I wanted this here because I think it will be helpful for you later. So this is in this part of the slide. This is what I have already mentioned, and it's something we commented yesterday. When I load my program in memory, what I'm actually doing is, remember yesterday the memory layout for my program. I'm just copying to the text section, the section with the program code. I copy in there my instructions. I am setting up the arguments on the stack. I am initializing, remember yesterday, the registers, the stack pointer and the frame pointer. So I'm also initializing those registers, and I just go to the first routine or the first method in my program, which usually is called main, and I copy the input arguments for this main routine. Remember that the arguments for the function, for the routines, for the procedures are placed in registers x0 to x7. Okay. So and then when the program finishes, of course, when this main routine or this main method finishes, the program finishes and returns the control back. So regarding the linking, we see that there are two different kinds of linking. One is static and one is dynamic. With static, what we are doing is that we place all the functions that we have written in our code, even if they are not executed, this will be there. And of course, the resulting file will be the size will be larger because it contains all the data. Even if those functions are not going to be used in my program, everything will be in there. For avoiding this, we have dynamic linking. This means that only the functions that I'm actually using in my program, that I'm actually calling at execution time, will be included. And this means that the resulting file is smaller because we don't have all this library there. In addition, if we update one library, this will also allow us to use that new library without recompiling or program. Okay. So I want to also show you how Java works in this compilation and execution flow. With Java, what is happening is that once we compile our program, we have like an instruction set of portable instructions which are called bytecodes and which are interpreted by something called Java virtual machine. So with this, we can execute our program in any host machine because the Java virtual machine will interpret those bytecodes for any given machine. We have, in addition, something called just-in-time compiler, which if the Java virtual machine thinks that some code will improve the performance if we compile it for the native host machine that we are using, then it just do this in execution time. So this is what we have commented, but again, I like this to be here in the slide for you. As we have mentioned, so the program is converted to something called Java bytecodes, and this is interpreted by the Java virtual machine, and this allows us to port those programs among different machines with different architectures and so on. So something important here is what we have mentioned, that if the Java virtual machine considers it, in order to increase the performance, it can compile in execution time some methods to make them run faster and perform better. Okay, so what we have seen today is we have seen pseudo instructions. We have seen pseudo instructions such as compare and move. We have also seen addressing modes such as the wide immediate operands and immediate addressing, register addressing, relative addressing, base addressing, and we have also seen what happens to my program since I compile it until it actually executes on memory. So now let me check if you have any questions. Okay, someone is asking recommendations for a book. As I have mentioned, the book we are using, that is the one that we are using in all the lectures, and is the one I always put in the first slide. This is the main resource for this module, and this book also has appendices in which you can see more details than the ones we are going to see in this first stage module. Someone is asking, are add-I and sub-I also using immediate addressing? Yeah, yes. So as we have shown here, so this I stands for immediate, and add-I, similarly to sub-I, are using immediate addressing, what we call immediate addressing. Let me check if you have any more questions. So someone is, for instance, asking why we will like to change with move set the other values in the other quadrant. So for instance, imagine that you want to initialize one register and you don't want to keep those bits. So maybe that's a reason for you, because you were using the register for any other thing in the past, and now you want to reuse the register for a different task. So maybe you want to initialize all the rest of the data to 0 for that. Okay, so many thanks for your attention. Tomorrow we will start with arithmetic for computers, which is chapter 3 of the book. As always, if you have additional questions, you can use the ticketing system, and we are there for helping you. And also remember that tomorrow at 1, the second lab will be available for you. And yeah, hope you have enjoyed this lecture, and have a nice see you tomorrow, and have a nice rest of the day. Thank you so much. Bye bye.